Yeah. Okay, how about this? Testing, 1, 2, 3, testing. We have lots I spent 20 minutes on that yesterday. Yeah, so I found out what it was. You can all mute, yeah, you can mute. So there's a microphone sound option, a volume option, and it was toggled all the way to mute. It wasn't my computer. Like, damn. Well, I can send them this link. And I just said damn on camera. Oh no. That's not good. Yeah, the link's up. Yeah. I'll just let that run through. Yeah. Hello.
Baby Matt is out.
Yeah, that's correct. This is the wrong repository. Let me get down to NL. Okay. And then ignore what I look at. All right. That looks too. Yeah. Cool. I can start eating. Does anyone have any questions? I don't know, when did you guys submit your Tableau homework? Or okay, you guys are done. Okay, cool. Oh, okay. Hey.
We have a podcast here, and you are welcome to join.
Yeah, you guys go ahead.
Eat something.
Yeah, thanks. You guys should go. Bond. Network. No. Oh my gosh. It's funny.
countdown.
Yeah, can you hear me? On there? Testing, 1, 2, 3. Testing, 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 1, 2, 3. Testing. Okay, cool. There shouldn't be so a downgraded kind of like seeing what's going on. You can also see on your screen once you access your the folder for today's lecture. Let me again just get everything going.
Put that same link. Put that same link.
Yeah, I should feed the same link. Does it work?
I did.
Okay. Okay. Oh, all right. Thanks. See the URL. And I'm just trying to access my own local repository, so let me get to that. Going. Oh, whoops. Get started. One's on mute. No, it's not. Oh, that's even worse.
Honestly, I'm not a poet.
That is odd. Okay, so that was bent. Yeah, yeah, yeah. Is that better?
No. No.
Okay, so at least.
What do you want to run? I have an extra computer. If it's just stuff off the web you want to run.
No, okay. It's just a connection issue. So this laptop doesn't have the right adapter. It's all good. Yeah. Do you have a HDMI to VGA? I kind of doubt it. Yeah, because to get a perfect clear picture.
USB-C?
Yeah, I think I should. Let me see. Please let this be VGA. Okay, let me connect that back then. Actually, I'm pretty sure this is gonna work. And then let me change. That's a good sign, right? Adjusting the image. Thank you. Oh my gosh, you're such a lifesaver. So, yeah, so this is a work computer, and I'm not gonna pay out of my pocket for an adapter for my work computer. L50. Okay. My other laptop has more options for ports. Anyways, excluding the technical difficulties, in your GitLab repository, please do a git pull. Addition to that, if you didn't read the announcement, do a conda install TensorFlow and then also Keras. If you have issues with that, we can discuss that in the first student exercise. As you're aware, Matt had some family matters, not an emergency. As I said, poor use of diction. Yeah, it's kind of funny actually. But what's not funny is his wife is in the hospital. I don't know what's the right word, in labor. Is that correct? I literally don't know. Like, yeah. Okay, in labor. Okay, so she's in labor. So that's exciting news for him, you know, and for all of us here. Hopefully, yeah, he gets this well. And again, just to test out my audio and video, is it good?
Yep.
Okay, cool, excellent. So let me come over here. So yeah, Dylan usually he provides notes, kind of like a summary of what's going to happen in the lecture, and then also some additional resources if you're kind of like stuck on some certain material. That'll be there in this like resources kind of heading. You've seen that before several times. I'm just kind of like detailing what's provided. So the goals for today is to understand the types of problems where neural networks work well, understanding Keras, and then TensorFlow, primarily just Keras. Kind of like spoiler, Keras is a wrapper on top of TensorFlow. So you're not using TensorFlow, you're just using Keras that's wrapped around TensorFlow. So that's if you're wondering why did I download TensorFlow, and then later on in this night you're like, we didn't even use it. That's kind of why.
Why were you not using TensorFlow?
TensorFlow, yeah.
You're not using?
Yeah.
Why?
Well, we're using it in the sense of Keras is wrapping everything around it. So you can like kind of similar to what was the past example? SQL Alchemy Flask. Remember that library? That was a wrapper around SQL Alchemy. So think of it like that. Just something that lessens that learning curve for you as a developer or a data analyst. And then later on, hopefully, I will try to get into the unsupervised learning section. It's just one algorithm or concept from unsupervised learning, which is k-means clustering. Yeah. And so wire neural networks excels at finding patterns in nonlinear data, also linear data. And then it's really good at problems of image, speech recognition, and then any other cases. Besides classification, it can also, you can use neural networks or deep neural nets and to do like estimations as well, as you kind of like experienced with linear regression. Throw that there for your output variable. Yeah, and then let me just open up a PowerPoint right now to kind of just go in depth what neural nets is and etc. So there's that. And then just a couple of notes for tonight's lecture. Personally myself, if things have slowed down, like I'm seeing that I'm going too slow, I will kind of speak a little bit faster. If you feel I'm speaking too fast, let me know. I can try to cool things down, take it slow, but every now and then I just go back into like go back and speed talk, talk pretty fast again. So just, yeah, please let me know. If you have any issues, let me know in regards to like installation for TensorFlow or Keras. There's particular corner cases. If some people have done that, has anyone had any issues with their installations of Keras or TensorFlow? It's pretty solid.
So Keras TensorFlow comes with that, right, as a package. Do you need to separately install TensorFlow?
Yeah. So imagine if you just install Keras. It's great. Sometimes when you run the your Jupyter notebook or your program, it will work a lot of times depending on the version of TensorFlow. Using the softmax function, which you'll see later on tonight, an activation function, it will not work because of the version of TensorFlow. And so that's why there's that conda install TensorFlow. Or if you need to update TensorFlow, just do conda update TensorFlow. Let me get the slideshow coming up. Does anyone have, and I just started, but does anyone have any kind of questions? Anything I said? Solid. Right now I'm just waiting for this PowerPoint to come up. Okay. So for the remote users, if you cannot see this PowerPoint, shoot a Slack at Bill, Daniel, or myself. And yeah, just let me know. Try and get that up there. Solid. Whoa. Oh, that's cool. Okay, I'm just gonna get out of that mode. It's kind of weird. All right, so let me start this presentation for the introduction to neural networks. So here, neural networks are used widely. There's a lot of open source libraries, not a lot, but there's a few noticeable ones, right? And then they're also widely popular. One is Google's DeepMind. I'm not sure if that's open source. You can let me know. But with Google's DeepMind, they're one example of using AI or neural networks is scan a million eyes to fight blindness with NHS. Don't know what NHS is. You can even merge two images together with neural networks. Recently, about a few months ago, there was one case of even changing, altering a video of, excuse me, let me rephrase that. There's a situation where, say, you know, a particular movie, call it Pursuit of Happiness. You can replace Will Smith's face with something else and make it look as real as it can be using neural networks or AI, so to speak. I forgot what the term was for this case, but it's had some like negative association with neural networks and AI just because of what happened. I can probably send a reference to that later. Yeah, that's neural networks can merge not just images but also videos as well. Neural networks, like I said, can do classification, so distinguishing a muffin between a dog and classifying the probability of, like, is this a muffin or a dog? I thought that was really cute. Yeah, so artificial neural networks. So when you think of neural, you think of sciencey words, something I try to get away from quite often, K through 12, and even after in college. I'm not trying to say anything bad about science. That just wasn't my type of thing, my cup of tea. Cup of tea. I had to. So yeah, the development of neural nets were inspired by the arrangement of neurons in the human brain. The neurons, or axons, is what is used to send signals to other neurons. This is your axons, I believe, and then they'll be sending it to your neuron. Again, don't call me, I don't really know.
The long part.
Okay, cool.
Try to censor yourself.
Cool. Long part. Yeah, cool. Axon, yeah, what she said. Synapses are sensors that receive signals from their neurons. And then you can see this analogy, if you will, of this sciencey kind of like neuron thing. It's totally incorrect on my my words or my wording. And then here you can see kind of like the mathematical translation of it, what a neural net would be to that of a neuron and everything surrounding it, associated with it. And here's just another example of what a neural network can look like with several neurons / nodes, and then hidden layers. I'll discuss that later. And then seeing this kind of like analogy with that with the brain, the human brain or whatever. As it turns out, the neural networks were programmed to find patterns in inputs in much the same way the brain does. You can again see the visualization of what would be your input layer going into these hidden layers to an output layer, and kind of seeing that association happening respectively. I don't know where the signals start and end in this connection, but you can imagine. And we'll also see a visual representation of what a neural net is in about like 5 minutes. The math. Neurons kind of sort of similar to logistic regression. You have some inputs, your features or independent variables here. You'll put some associated weight with them. And then from there, you put that in this function. Just as you've seen in logistic regression, that little formula, hopefully that was covered.
What's B represent?
Huh?
What does B represent?
B?
B.
B, yeah. Awesome, yeah. So just like within linear regression, logistic regression, you have this bias. So B is bias. It's the encompassing components of an estimated error. It can be biased to your model, error from your model, or kind of like some error due to something else. Yeah, there's like different components to a bias. So B is equal to your error term of the model itself, plus like some other type of errors. You might call that it's alpha. I lost track of my notation, but yeah, that's what it is. And then here you have your weights multiplied by your vectors. The capital X is a representation of a vector, your independent values. So this initial weight times x1 plus the second weight times x2, kind of like you've seen in the multilinear regression. Did you guys see that on day 1 or day 2 this past Saturday? Okay, yeah. Yeah, I know. Everything's like going so fast. You're like, I don't even know anymore. Still understandable. That's the bootcamp lifestyle. And then you get your output. This output of the neuron right here is equal to your y, your resulting vector, and then function with all of its components. Any questions on that part, actually? Okay, cool. Yeah. Yeah.
Equation pretty much applies for the neural networks. Is that the equation that's applicable?
It's not the exact equation. It's kind of like, this is kind of like a little example of what the gist of it is. The algorithm itself, and it can vary depending on the type of neural net you're creating and the type of, and the different parameters you'll have in your neural net. And you guys will see that later on.
What kind of function you don't know, yes? What kind of function is it you don't know?
Yeah, so that just depends on the neural net you're creating. So yeah, I'll discuss that.
Okay.
Okay, and here you see the neural network. So just a layer of neurons connected together. So this is all segmented to show what the encompassing neural net is. You have your input layer. These are your features. This is your bias here. And then these lines are your neurons or synapses, whatever, are your weights with subscripts of like 0, 1, 2, 3. So weight 1, 0, weight 0, weight 1, weight 2. In the input layer, you have your hidden layer or layers. You'll see that later on this evening. What the hidden layers are. And in these nodes of this hidden layers, there'll be calculations. And then outputs are of these nodes probabilities. And then you have the output layer. So what you want your y to be, your y vector, with an output of probabilities of whatever you're trying to classify.
Is there another bias within the hidden layer as well? The diagram is.
Yeah, so I can't fully answer that because from what I understand, and I don't know who created this visualization, I couldn't find a reference for this visualization, but this should have been x1, x2, and then however nodes you want. One of them necessarily doesn't has to be a bias node. So that's a little bit deceiving. I think what the author of this visualization wanted to show is like there's also this bias, but two things. I can't properly say why that's there. I'm pretty sure it's incorrect based on whoever created this visualization. Any follow-up questions there? Okay, yeah. Cool. I can also, double check, is there an actual bias node for every layer, excluding the output layer?
Generally, there is.
Hmm?
Generally, there is a bias on every.
Okay, generally there's a bias. Okay, cool. Yeah. So we gotta have that information there. Typically, I know for every usually I deal with regular models, anything non-neural net, usually it has some associated bias, that plus B you guys saw. Typically that's there within every function because there's you can never have a perfect model. That's why you have that plus B there. Oh yeah, maybe that plus alpha is uncertainty.
So the way I think about it is,
there's
an infinite number of lines.
Yeah.
Not all lines go through 0.
Exactly.
So
yeah.
If you have a bias of 0, that implies all your lines.
Exactly. Yeah. So there's always some amount of uncertainty. There no exact solution, right? And you'll see that whenever you go through several courses, you always see this kind of reinforcement of just knowing that there's always uncertainty within models. I have no idea what I just did right now. Right here? Oh my god. Yeah, so I'm not going to go into, basically I'm familiar with the software. So the most important mathematical detail to understand is that neural networks typically output probabilities. As I mentioned, your output would always be probabilities. In other words, if you were to tell how many hours we studied for test and our grade on the midterm, it will spit out the probability that we pass or fail the final. And you can see this kind of reinforcement of a visual reinforcement of a probability being in your output of this output layer. So how does it work? Neural networks are trained by feeding it forward propagation into the hidden layers and then to the output layer. And then there's this backward propagation as well. And then in this forward and backward propagation, it's an epoch. I'm probably saying it wrong. Someone can quote me, though. Epic? Hey, I like that.
It's a potato picado.
I'm gonna call it epic because that's epic. Yeah.
Very bold trees.
Yeah, I haven't actually checked the right pronunciation, but you'll see that what epoch is later on. So don't worry about that. This is repeated until the neural net learns how to provide an accurate probability for a given input. And in this case, it's a vector representation of what an image would be. Hopefully that was kind of like mentioned in last class. Images can also become, they can be converted into a matrix representation of an image. I could probably find an example for that later on. How does it work? A trained neural network can take a new input, picture of a dog, and feed it through the network to predict the output label. And you can see this input layer, there's like a gargantuan amount of information. Inside these hidden layers, activating neurons occur, and then you get your little output layer. Kind of think of it as an analogy. In the gold rush, people would like do the thing with water and filter out sand to find their gold, and your output layer is your gold. It might be a horrible analogy because yeah. Anyways. In a nutshell, at first you don't, and then for some reason they just left it as a that. So that's a little bit weird. I just did that again. Okay, cool. Any questions on the neural nets material I just discussed? Solid. Okay, so why keras? Who keras? As I explained, TensorFlow. So TensorFlow briefly is a machine learning library. It is used to build neural networks. Runs on multiple platforms, including a distributed computing system. So think of like instead of one machine, you have a distribution of machines computing and going through your model. Think of it like that. That's what distributed computing is. And then TensorFlow allows detailed fine-tuning of your model. Kind of like. Keras, it's a layer of abstraction, simplifies deep learning modeling, allows rapid prototyping. It's pretty lightweight as a wrapper of TensorFlow. Just went back. So Keras allows interaction with TensorFlow through a simplified interface similar to sklearn. So the library y'all love for machine learning. Keras provides that equivalent simplicity as well, and we'll see that in the working examples. And then here's just a little like snippet of what you'll be working through later on this evening. Okay, installation, conda install Keras, and then the conda install TensorFlow. I asked you already if you're all good, so I'm glad to hear you guys are all good. I had 3 different types of errors yesterday. It was fun. One of them I couldn't resolve because the person had a Windows 32, Windows 7, and it was like 32-bit TensorFlow always installing. So that was a hard technical issue and still pending. I'm trying to resolve that. It's kind of, and then here, I'm going to stop here. This is the k-means portion of the lecture. Hopefully we get to that. And now I'm going to go through in about 10 seconds, and we'll start our first working example. So brief intermission. I'm going to go to folder 1. So if you all want to get to machine learning folder, day 3, activity 1, go for it. If not, you can also watch me. Yeah. Oh. Okay, let me see if. Awesome. So before going through that exercise, I actually forgot I was supposed to go through a kind of visual representation of how a neural net works. So I'm going to go through that by going to this link right here in the notes. I'm going to send this to the resources channel. Do you guys have the? Yeah, you guys should. I'm going to send this to the resources channel right now. And then we're going to have fun with a visual representation of two different types of provided data sets on TensorFlow.org and see how a neural network works. Where's my mouse? Okay, so we're going to start with this data set. If you're there, please just click that little box. What would that data set be like? Just imagine a collection of data where, and then there's two clusters. That's the best way I can explain this. If you need a working example, I could try to find one online where you'll have two clusters on the X and Y axis, or two-dimensional kind of matrix. Right here we have our two features, right? Here we're just gonna have one hidden layer, and then I don't know, I'm gonna throw like 6 neurons or like 3 neurons, I don't know. And then we'll have our output layer. So typically, or all the time, neural network, you'll have 3 layers. It will be your input layer, containing your features, the number of features you want to input. All these are, every feature is a vector of numerical values. It can never contain strings, so kind of keep that in mind. You'll have one hidden layer in your neural net, and then you'll have your output of how many things you're trying to classify. Later on, I will show another example, and it'll be a deep neural net. And spoiler, the deep neural net is just 2 or more layers. Yeah, I'll get to that soon. Okay, so let me run this, and then here we're going to see the number of epochs run pretty quickly. So it's the forward-backward propagation. That's an epoch, epic. And then at the same time, we'll see a test loss and train loss kind of visualization start kind of like linearly and dramatically decrease, kind of downward sloping like this. I believe that's like a function of 1 over x, so kind of like the visual representation. You'll see that occur pretty quickly. And then you also see the classification occur in your output layer. Starting it, boom. I'm going to start that again. This is pretty quick. So again, this graph, you'll see it kind of be downward sloping. And then you see the classification occur where a boundary is created, and then number of epochs running. Amazing, right? And then you'll see from the input, inputs going into this synopsis, if you will, the weights will be adjusted accordingly through every epoch. Right now, the epochs are growing pretty fast. Yeah, and then your output, you see this like quick classification of your data and segmented as so. So this is an example of a linear data set. So what's great about neural nets is you can quickly classify information of nonlinear data. And so, sorry, I'm distracted by the Slack channel. Okay, cool, got that. Sorry, I should probably not look at the Slack channel. All right, so we are going to look at a nonlinear data set with one hidden layer, I don't know, 5 neurons or whatever. And we have the same number of features. And then we have our output. And then I'm just going to run this. And then we see here the classification occurring here. For a large number of epochs compared to our linear data set, we're still seeing our test loss, train loss decreasing ever so slowly as we get above 100. And then we see this classification occurring right here. But we're not, quite there within our classification. So what happens if we decrease the number of neurons? So we have our 3 neurons. Run that. And then we still get that same classification, but you can't hopefully see it rotating at like 300 to 400 epochs. I'm just going to add some noise as well. So go. And the classification so occurs. So, interesting. So here, yesterday I was working through an example with the students from the Monday, Wednesday class where this classification would occur, but it wouldn't quite classify everything correctly. There was just this classification where it went like this. An orange section like this, and there was misclassification. In the case of a nonlinear data set, the only thing you would need to do is just add a hidden layer, and from there you're able to bring this abstraction of nonlinear data, simplify it, and classify it even better. So I'm going to run through that. You can see for a less number of epochs or number of forward and backward propagations, you quickly get your classification straight off the bat. So about like 20 epochs, and then from there, you see already the parameter of classification is there, and it's basically all correct. Right? Yeah. So that's the visual representation I wanted to show. And then here with this additional layer, this is our deep neural net because we have this second hidden layer 2+. Think of it like that.
What are the functions of the activations regularly?
Yeah, definitely. So for here, you have several activation functions available to you. It's with respect to TensorFlow's library. You can use other types of activation functions, but these ones in particular are ReLU, hypotenuse tangent, hyperbolic tangent, sigmoid, and then a linear activation function. In the notes, there should be an article with a distinction between these types of activation functions. I can, go straight off the back and show you at least 3 of them. Sigmoid one, I can't visually represent just because I haven't done any research into it, but the ReLU function will, this is your x and y axis here. For any values less than 0, for any x values less than 0, it will stay at 0. Yeah. And then for any inputted y values, you'll get y values where it's like y is equal to that y equal to x. So that's a ReLU function. All right. Earlier, for any x values that are negative, less than 0, they are 0. Anything after that, pop 0 or up x values, it's y equals x. And that's the ReLU function. It's widely popular to use in an activation function. I have no idea why, but a lot of casual competitors like to use that. And then let me do the tangent of each function, and I believe tangent h was like that, where our values are -1 and 1, and then you can see it go from negative infinity to, or yeah, x values of negative infinity to positive infinity. Once you go positive infinity, it'll say like a value of 1, negative infinity. Your kh function will go to -1. And then there's linear functions. So linear. All these functions listed above, they are monotonic, and then they're also they can have a derivative, so there's no like gaps in these functions. Not too much because you're like, what the heck is this talking about? Stats. Yeah, but those are the activation functions are. I'll provide that link in resources channel later on of the distinctions between these activation functions, and later on you'll see a couple of other ones as well. Yeah. All right, so now let's get started with the working example once I get there. Bill, am I still good with the video showing? Nice, very cool. And then remote people, any questions? Okay. 1, 2, 3, 4, 5. Cool. Okay. So before we start, I'm going through and creating our neural net or our deep neural net. We're going to go through one hot encoding. So that's a way to transform your output vector. Transforming that, say you have in your original data set a target column with a bunch of strings being like not a dog and then a dog, or muffin and dog, right? You'll have those strings in your data frame for some target. And then you'd want to transform that information to something numerical, so that way our neural net can compute the outputted probability of your target being a dog or a muffin. Okay, so we're just going to go briefly through this pre-processing. Here, just kind of discuss why we pre-process, transform data to better suit the model's underlying assumptions, and the format the data the way the model expects. Right here, better suit the model's underlying assumptions. What do I mean by that? Yeah. It's not covered, at least up until now, and then also in the 4th day's instructions, but every model has underlying assumptions about your data, about the data, and it can range from the number of features. You want to make sure they're not collinear, whatever. Yeah, I forgot the terminology there. You want to make sure the distribution's well off, not skewed by, when I say skewed, do you guys know what I mean? By one person?
We'll elaborate on it. There's different skewings.
Totally. Yeah. So there's 2 different types of skewed data. So I'm going to start off with a normal distribution.
Toss that one out, please. Just toss it out. Kill it. Thank you.
Ooh. Play basketball.
Forget the programming career.
I'm gonna Lakers.
I'm sure you have the hype for it.
I'm probably gonna burn my jerseys. All right, so here's a normal distribution where at the center of it, your mu, or your mean, is 0, and your standard deviation would be some number of standard deviations. It's kind of like 4 ticks. Understand what a normal distribution is. Okay, so hopefully the red mark works. Okay, so there's two different types of skewed data sets. There's all right, so that's kind of bad actually. So this portion right here, this is a right skewed data set where all your all the data is centered around a mean of 0. It's now centered at a mean of like negative whatever, negative x. And in textbooks you'll see like negative mu. And then to remember, this is a right skewed data set. Just think of everything right here, it's all gone. Skewed. And then this dashed line you can like barely see. Everything to the left of this, that's left skewed. And then the cluster of data centered around your mean from the normal distribution, it's all shifted to the right because say you have more of your information is tending to the right. What was that? Pre-processing. Yeah. So yeah, there's underlying assumptions for every model, and this is one of them. There's several other ones. I can find them for you, but typically they're in statistical textbooks. And then, did you guys cover standard scalar on Saturday? No? Okay, so actually, since I'm on this topic, say your data set's right skewed or left skewed, standard scalar transforms the skewed data, whichever skewed, into something that's not normal distribution, but a Gaussian distribution, where and a Gaussian distribution is similar to normal distribution, where I believe it's a little bit more steeper. The Gaussian distribution would be a little more steeper than a normal distribution. It has a mean of 0 and standard variance, standard deviation. So that's what the standard scalar does. And when you're pre-processing your x variables or your independent variables, your features. Yeah. All right. So let's get on back to the pre-processing for our target vector, our column, y column. So here's an example of these vectors, and just a little bit of note right here, since you see this bold notation. Inputs to neural networks, again, are vectors. They're not floats, integers. They are vectors of numerical values. And then here's one great example of or two great examples of vectors, and then a bad example where here we have our target being strings. Crazy, right? So let me just run that through real quick. Just what time is a lot. One on hop encoding. So the data set we're going to use right now is a famous data set of the Iris data set. And we're going to use this right now in our neural net. Let's get started. So, and I'm assuming you guys have your Jupyter notebooks up. Yes. So here we're going to create our data frame. Here, let's show the end portion of our data frame. Here, our target, our class, has strings, right? We want to be able to work with numbers, even with our target variable or vector. And this class contains 3 values. So we're going to encode these 3 values into a series of integers, 0 being setosa, 1 or being vesicular, 1 being that first row, and then so forth. So we have this encoding occurring for our strings. And that's the similar process that was done in logistic regression seen this past Saturday. Okay. And then for one hot encoding, you will do the label encoding using sklearn, and then one hot encoding using a Keras package. Okay, so let me just briefly read over this. Label encoding changes these three classes to 1, 2, 3, respectively. One hot encoding, we then change each row's class of these 1, 2, 3 classification of integer values into vectors. These vectors are shown here. They're like a series of values that are true or false. So this 1, 0, 0 right here, that means Aristatosa, not verisecular, not Volcanica. So say Aris Volcanica, that would be not verisecular, excuse me, not Setosa, not verisecular, not, and it is Volcanica. So one hot encoding changes these values into vectors of true and false values. Okay. And then here we're going to change our data into a matrix and partition it. Here we do a label encoding. Here we instantiate the object label encoder, put it into a variable. We fit the label encoder with our target vector or array list, right? And then we encode it. We encode this label encoder by dot transform of that y value. We fit it, then we transform. So to kind of remember, fit, predict, as you've seen in your models in the past classes, except here in the pre-processing, you'll do fit and then transform. And save this transformation of your encoding into some variable.
So while doing the transformation procedure, it would automatically assign value 0, 1, 2, 3. Yeah.
Yeah. So so from what I understand, I haven't really looked into coding itself. You're fitting. So you can y. We see we have like 3 values. This is like my assumption. And then for these 3 values, classify the respective strings, and then do this mapping of original target call vector.
So the encoded Y will be like a 3 by N matrix?
I believe it'll be
For this?
like an n by 1. I'll find out. Let's find out actually.
Well, okay. No, it should be.
Cause yeah. So the reason I say that is because of matrix operations. It's a big word right there. In linear algebra, there's something where whenever you're multiplying 2 matrices or counting some operations, plus x and y. That's fine. We'll have like a n by like n, let's just say matrix for x, and then right here for y, you have like n by 1. Here, this outputs some vector z. Yeah, z, and then this would be a n by 1. Yeah, n by 1 matrix. So it's there's these properties of matrix and vectors happening inside these methods in sklearn. I am curious what the dimensions are for encoded y. What is it like that? So 150 by 1. Our data set was like 150. Yeah. So. Well, put my mouse up there. You see, this is the n by 1, 150 by 1. Okay, and then here we're just gonna go through a for loop and show the respective encoded y with its y values. gonna run that. We see here isotopes 0. And then once I get to some point, our secular is like 1. Right. Cool. And since we have that encoding, now we're going to do the one-hot encoding. One-hot encoding is simply from keras.utils import to categorical. One-hot Y to categorical. Input your encoded Y. That's it. And see that run through, assuming your TensorFlow works. You'll see the respective the respective encoded Y become now the one-hot encoding. So whatever was 0 or one of the flowers is that one value 1. And for Tanica, say this is for Tanica, once that occurs, also it's like a value 1, this is 0 because they're true false values. Any questions about one-hot encoding? It's kind of pretty straightforward. So again, in summary, label encoding, one-hot encoding, if your Y vector or your Y column or your target vector contains a bunch of strings. Yeah.
So do you use the label? So here you're using the label encoding essentially on your output layer, but this is your Y.
Yeah, this would be my Y.
What you're pointing at is the one-hot.
Yeah, exactly. Yeah. So the labeling of
like up above.
Yeah. Oh, sorry.
This one is you're using the labeled encoding for your Y value.
Yeah. So here I'm showing the encoded Y. Excuse me. The label original class. So we're showing the original class right here as for secular, and the encoded label is a value 1, or in that range of values. Yeah.
What does one encoding?
What does that mean?
One hot encoding, what it does?
Yeah. Not so it's kind of like weird little thing, like what's going on?
Yeah.
Yeah. So say. So here we have like our original target column. Here when we do the encoding, we'll have 0, 1, 2.
Yeah.
Right? There's this mapping happening right there to numerical values. And then for your one-hot encoding, it doesn't spell anything bad. Just want to make sure. Sometimes acronyms can spell bad. It'd be the same vector of like vectors within it. So it'd be like a matrix. Vector, sorry. So here, that first row would be 1, 0, 0. And then what would be the next row? Can you tell me the
0, 1, 0.
Yeah, exactly. And then lastly, we have that. So does anyone have questions about one-hot encoding, how we got there after this, what I've just shown right now? Solid. To the remote users, I'll post up an image of what I wrote on the board pretty soon, or yeah, I'll do that later.
Silly question. Do people know why you use one-hot encoding?
If you do your research, oh well, sorry, not you, sorry. If the user, yeah,
it's one of these weird things of a solution is being presented to a problem that people don't understand potentially.
Yeah. It's hard to say on person to person in their background. Like,
I guess I see it as a way to transform categorical data into a number matrix.
Number matrix, yeah, exactly.
Is, if you have 5 categories, how do you distinguish that in numbers?
Yeah, definitely. So it'd just be a longer, say if you had like a vector with like 5 different classes, it'd be just that one matrix, and then just a longer row. So say you have like, there'll be 5 elements, and be like 0, 1, etc. happening there. And then respectively, you have 0 through 4 for whenever you encode the original target column. And you'll see that later as well. Yeah. All right, so I'm gonna go into folder 2 right now. I think that's an exercise for everyone, right? I'm just we'll go through this together, and then on the 3rd exercise, I'll have you slightly do it independently. So let's start off with this. Where's my mouse? This exercise. We'll just get there. I lost my mouse. Why is it white? Oh, it's black. I really can't find it. Okay. Anyways, so here we're gonna, this is the solution. I'm trying to pick things up because I think I talked a lot. So we're gonna import a data set from sklearn that that sklearn provides and or generates. So the number of features we have are x vectors. There's 3 of them. You'll have 2 classes for your y or your target vector, and they're your x and your y vectors or columns or matrix vector are created, and then we're going to do a reshape on this this y variable because here within creating this data set, we just have to do that, and to make sure we have the correct shape of both our x and our y. And again, the reason why we want that same shape is because of doing matrix operations like I kind of showed above, or to the left of you guys. Now we're going to use the train test split to create the training and test data with the random state of 1. And then we'll do our pre-processing here. How would we start our pre-processing for, I guess, our target column? Until you see like the what's inside the values of the y vector. Those are just numbers. So we're fortunate enough to skip the encoding and only focus on that one hot encoding for our target column. Yeah, so that's pretty convenient. So you guys don't have to like do that encoding step for a good portion of this evening. Here we're going to do a transformation of our features, or the matrix of our x vectors. Why would we want to use standard scalar and transform this data? Yeah, that's right. Because like I mentioned earlier, say we have an a non-distributed, uneven distributed data set, we want to make that distributed. In particular, we want to make that the data set a Gaussian distribution where it has a mean, the center is a mean 0, and then your variance or standard deviations, or like unit standard variance or standard deviations respectively set. So we're going to do that. We're going to do the fitting first, and then
for all of the
It definitely helps out. Yeah, definitely. It would help out in your underlying output layer and making the correct probabilities of your output layer. So it's preferred, required. Yeah, it's nice to have if you ever want to be number one on a Kaggle competition. Not that I encourage you to do Kaggle competitions. That's I'm also not saying don't do Kaggle competitions as well. So yeah, do what you want with machine learning or AI. You can also build your own product. Side note, on LinkedIn, I see like several videos of people building their own products where they use AI to do simple things like identify what sign language gesture would occur once you put it out in real time. So if say, for example, like, I don't know, sign language, I'm holding out like something where it's like a dog. In sign language, I can use a neural net or deep neural net to have wherever that personal project be done. I'll find a video either through LinkedIn or YouTube. I kind of see a couple of those every now and then. They're pretty cool just to see that people have the capability now to do that, like to build those kind of like low pet projects. Or yeah. And then so now we're going to do a one hot encoding after doing our transformation of our features. So from keras.utils, import to categorical, and then we do the to categorical for both our training data and our test data. That's going to run through. And then now we're going to create our model. So first we decide what kind of model to apply our data. For numerical, we use regressor model. That being said, where a regressor model is where you want your output to be some like numerical probability of estimating something, not doing a classification. For categorical data, we use a classifier model. Throughout this night, we'll be using the classifier model. And I'll kind of drop some like subtle things about the regressor model as well, and very lightly. So from keras.models, we're going to import sequential. Sequential, again, is that classification model we're using. So we instantiate it with parentheses. Next, we add our first layer. This layer requires you to specify both the number of inputs and the number of nodes that you want in your hidden layer. Here, we will have we're going to use our layer module dense. So keras.layers import dense. The number of inputs, we want to read the number of hidden nodes 4. And then after instantiating the model, for your first model.add, you're adding that first layer. You're simultaneously creating your input layer and one hidden layer in that one line. So our units, our hidden layer units, number of hidden nodes. For the input layer, that parameter in dense is input dimension. That's going to equal our variable, which is the number of inputs.
When you use dense, how do you add dense? Is it dense?
Yeah, dense is just a layer. Method. Yeah, method. Huh?
We have multiple. It has multiple.
Oh, like multiple parameters in dense?
Multiple denses.
Yeah, so you can have multiple denses in like separate model.adds. We'll see that a little bit later, or maybe if you scroll down, you'll see that. Yeah, here simultaneously we're creating our input layer and our hidden layer. And then here, our final layer, which is the output layer, we're going to do another model.add, having that dense method or object. Yeah, object, sorry. Object with the number of units For our output layer, it's the number of classes, which is 2. And here we have an activation function of softmax. And here, notice we have an activation function of ReLU, or ReLU.
Rectified linear unit.
Exactly. Rectified linear unit. That's what ReLU stands for. Within our ReLU, the activation function, this activation function applies to the hidden layer. And then here your activation function softmax will apply to your output layer. This is a distinction of softmax, tangent of H, and several other activation functions here in the output layer is the activation you use to what you're going to classify, or excuse me, how are you going to classify your output layer, depending on the number of classes you have. So here I have 3 classes, so I wouldn't use softmax because softmax is optimal for classifying your output layer of with 2 classes. I believe hyperbolic tangent, what allows you to classify classes 3 or greater, seen here on the board, A, B, and C, being our classes for that target vector. And then here we have our model summary. This model summary just shows the number of permutations that's occurring in our neural net. So here in the first layer, we have the number of parameters, which is 16. And here we have a number of parameters being 10. So that's like the number of permutations. The way it's calculated, it depends on model to model. When I say permutations, some of you may recognize it. You think of the typical probability permutation calculation. For some other models, that calculation doesn't hold true. And I'll show what this and other kind of data sets are visually. So now we're going to compile the model. So we very quickly we went through and we added our input and hidden layer, right, in this one line with an activation function of ReLU, rectified linear unit. And then we added another layer, which is our output layer using softmax. Okay, and now we're going to compile the model after adding those layers. We're going to use an optimizer of Adam. Adam is a certain type of algorithm. I've tried looking up quick documentation about what Adam algorithm is. The only I've had is an extensive article that I didn't have time to read through, and even then, the calculation itself was pretty extensive. So I can probably provide that later on, and if I forget, just remind me. But we have an optimizer algorithm, Adam, a loss function of a catechol cross entropy. If you're using the regressor model, not the classification model we're using, you'd use a loss function of MSE, as you see in the comments right here. The sense for mean squared error. So that kind of rings a bell to some of you in regards to linear regression, logistic regression, and some other statistical computations. MSE, that's what you use in the regressor model. And the metrics we want in this array are just the accuracy. Run that through. And then now we're going to train the model. So compile. Now we're going to fit our model with our scaled inputs and 746. And our transformed or preprocessed / one hot encoded target vector. And then here we have the number of epochs we want. You can put 100, 1,000. Kind of depends on how far you want to do your computations on your local machine or your distributed system, or maybe you care more about the higher accuracy you want in your model. So the more epochs you want, or forward and backward propagations, the higher probability, or excuse me, higher accuracy you want for your model. As we saw earlier in the TensorFlow.org playground. I'll show that again. And then here we're going to shuffle. That just basically means for every epoch or epoch, we're going to shuffle our data. And we would want that, right? Yeah. So that way we can adjust our weights accordingly. And so that's what happens throughout this process. Seeing now. So here you see an accuracy of like 30%, loss of 0.93. For every epoch, when a shuffle is made, forward and backward propagation, every shuffle is made, you see the accuracy increase. I was going to say something right now. Just blinked. And yeah. So for every epoch, it goes through this process, and the weights are being adjusted accordingly. And those lines you saw of your neural network, those lines being your W's, they're being adjusted in this process. Going down, we see we're going 42%, our accuracy is 57%, and our loss is decreasing. Loss, this loss value isn't associated with accuracy. That being said, directly associated. So it's not like 1 minus the accuracy gives me my loss. That's not the case. Loss, I believe, is calculated differently for some models, but think of loss as the average of your predicted probabilities, I believe. I would have to check up documentation on that. Or if anyone would like to let me know, correct me, just let me know. Huh?
What the loss is?
Yeah, the loss.
I think it's the categorical cross-entry.
Oh yeah, but is it, how would it be calculated, or? Yeah.
If it's close, if one model is close to the line,
Yeah.
it's going to have a low entry.
Okay.
If it's spread out, it's all disordered, it's going to have a high.
Okay, so more like I could think of like variance, or kind of like variability. Okay.
How I think about it is kind of like it's kind of like a squared error.
Squared error, similar to that of like MSE.
Like if you were to write out the error equation of a squares fit.
Yeah.
Where you have y minus y hat squared.
Yeah.
That's essentially a loss function.
Okay, definitely. So I forgot your name. Scott. So what Scott said is think of your loss function like a minimizing the squared errors for your data set. And again, it's not directly associated with our accuracy value. Yeah, went down. So we're going to quantify the model. Here we use model.evaluate, and then we input our test scaled and our Y test categorical, and test our model, right? So model loss, comma model accuracy, using this print function with the format string. Our model loss is 0.49 and some additional decimal values, and our accuracy towards the end of the number of epochs, which would be 1,000, is 83%. And then let's do a quick prediction using predict classes. So say we just want to do a quick estimation for some array, or kind of like an array of arrays. We get for this array right here, a predicted class of 1 being whatever one was classified in this data set. I think it was reverse secular, if we're still in the, okay, we're not. Yeah, so 1 being the class of value 1 for our Y values. Let me just show like what Y values. Yeah, so it's just Let me get a 1. So yeah, it's that 1 value. Any questions about building a neural network? Cool. So we create the model or instantiate it. We add our, I'll probably show this visually as well. We add our hidden layer and our input layer simultaneously using an activation function, and then we create the output layer right here with a the number of classes we want, which are 2, right? And there's 0 and 1. And so this is a 3-layer model. So what we saw right here, we have 2 features, right? Was it 2 features? So, okay, we have 3 features. 3 features, and then we had 4 nodes in our 1 hidden layer. Remember, this is a neural network. Anything above 1 is a deep neural net. Okay, I think I just said 4. Short-term memory. Okay, and then run that through. I believe this is the exact data set, but you can just imagine what's going on. The classification is being done in this neural net. I'll leave that there. Questions? Awesome. All right. And then I'll have everyone go to the 3rd folder. Does the 3rd folder contain the answers? If so, I'm totally down with all going through this together again. If not, if there's no solutions in this, this 3rd folder, then we can just like take a 10-minute like coding little session. Are solutions there?
Yeah, it's solved.
Yeah, is it solved? Sorry. Is it solved? Okay, it's solved. Okay, so I'm gonna work through this right now. And next exercise, I'll give you guys like 15 minutes or 10 minutes to work through that independently. And then, yeah, let me get started. So here we're gonna import pyplot, LT, and NumPy, and then sklearn.datasets. I think you kind of typically see for your imports. Create our data set with some noise, some factor. Quite don't know what that means in a random state of 1. So that way we produce the same make circles data set. And then we're going to visualize this data set. Just like you've seen in the TensorFlow playground, I'll go through that visualization again after working through this exercise. So we see a nonlinear data set. Like, well, no, what are we going to do, right? Before we kind of think about that, let's start going through with the our kind of like pre-processing. We use train test split to partition our data, right? So let's do that. Here our training data, I believe, is 75% of the original data. The remaining 25% is our test data, X and Y respectively. And then here we go through with our pre-processing of our features, right? Skewed distribution, want to make it Gaussian / normal. Okay, so we're going to fit the training data for this object. And then here we go ahead and go through and do the scaling of our features with xscaler, this object dot transform. And then here for our y values, since they're numerical values, kind of showing right now, we have the luxury to not do the encoding and then go through the one hot encoding. I'm not saying that's hard or kind of difficult, but we can kind of get rid of that nuance. Say if our data set's really large and that processing kind of like takes some time. I already did that. Transform. Right, and so we're going to do one hot encoding using tcategorical from keras.utils. Okay, and then that's being done. That has been done. And as you see on the board to your far right, one hot encoding turns these numerical this encoded target vector into a matrix where everything inside it is just a series or vectors of true and false values. So here we simultaneously import our sequential model for our classification model in this neural network. And then we import the dense, quote me or don't quote me, object from keras.layers. We instantiate our model. And here we do two things in this one line right here. We both create our input layer and our hidden layer. Let me go back since these, since this data set's kind of equivalent to what we're seeing right now. So, yeah, so right here in that one line we just saw, we're creating our input and our one hidden layer. With our hidden layer having 6 neurons / nodes, and our input dimensions or features, it's a value 2. Hint model.add that output layer with an activation function of softmax. Softmax again is used. This activation function in the output layer is used for optimizing our classification with respect to the number of classes we have, or with respect to the model itself even. Okay, and then we do a model.summary. Here in the first layer, the number of permutations or number of parameters we have. The first layer is 18, second layer 14, total parameters 32. Here we compile the model. Optimizer equals Atom. The algorithm, the optimization algorithm I mentioned before, a loss function of using a categorical cross entropy, and then metrics. The only metrics we want are accuracy in this case. We fit the data using our test data, and then we want epochs to be 100. It could be 1,000 even, but say depending on the small size of it, we don't have to go through the number of classifications, and then shuffle being true. Go through this fitting. Let me show you the output. Here our accuracy is 50%, kind of going down. It's decreasing quite dramatically. You're like, oh, what's going on? And see here it's increasing again. So it's a little bit strange, right? You always anticipate as the number of epochs or epochs grow, you'll see our accuracy. You think our accuracy would always increase. That's not the case because our data set is nonlinear, and since we have one hidden layer, and sorry,
the accuracy.
The keras accuracy.
Accuracy.
Yeah. What about it? Sorry.
Is that R squared?
I would say R, because R squared is a
But is it a nonlinear model?
Huh?
It's nonlinear, right?
Yeah, it's nonlinear.
So the R squared was.
I think no, it's not R squared. Sorry, it's the accuracy of the model itself. So
But what is that?
what determines the accuracy?
Yeah, that accuracy is the percentage of depending on the calculation. I haven't checked it myself of how many correct guesses you got or true positives divided by the total true positives plus false positives. Sorry. And then the accuracy itself, it's not R squared or R, no, I believe. Yeah. And then it's more of like the accuracy of the model itself. Yeah, the probabilities and
There's probability.
no, I'm sorry. This isn't. That's a good question. I'm gonna hold off on that.
Let's say it's
Yeah. Let's take it as a. Yeah, I'll actually double check that. Question. Yeah, the accuracy of the model. And it being R squared, asterisk, not sure. If someone can let me know. Let me know. All right, so now we're going to compare this model to deep learning as we a deep neural network. So here we solve for this nonlinear data set. So what's supposed to happen is there's supposed to be some misclassification going on. I don't know why it's not doing that, but okay, that's cool. If you're ever trying to create a model like this, whatever. But yeah, some misclassification would occur in the say in between 0 and 663 epochs, and then it would increase again. So yeah, so remember from nonlinear data set, we'd want to add another hidden layer to adjust accordingly for data sets that are more complex, in particular nonlinear data sets. So how do we do that? And what's really crazy about using Keras is how easy it is to use. So we'll create the model. We're going to add our first and second layer being the input layer and the hidden layer with an activation ReLU. And then to create another hidden layer for this data set seen here in this example, all we have to do is add another line. And all we got to do is just put units equals however many neurons you want with the same activation function. So here, how many now? 6. Cool. And then what we'll see is, oops. We'll see the number of epochs it takes, or epochs it takes to classify this model, classify this data correctly, the data set correctly. It's going to dramatically decrease for adding this hidden layer for this nonlinear data set. So let me run this through. We see we have a lot more parameters since we have another layer. We're going to compile the model, and then we're going to do a fit with number of epochs equal to 100. And as we go down, starting within our first epoch or epoch, I'm going to use that interchangeably, I guess, tonight. Accuracy is 0.49, and we see it just increasing. And you'll see that slight decrease as we saw earlier. And then also, what's another thing to note for this, say, epoch like 40 or epoch 40, above for that neural net, it was like accuracy of 40, and then not even, even on the first epoch, we had 0.49. So adding that hidden layer substantially made our model adjust accordingly in its calculations, and those weights were also being calculated accordingly. So right here, reset, play that tape back. Okay, our weight is 0.18 right here, and our weight is 0.42. Let's see what happens right there. We see our weight being 0.55, and then our weight being 0.43. So in this number of epochs, or forward and backward propagation, we see our weights being adjusted accordingly. Yeah. And that is our deep neural network, or deep learning, as you hear. And here we're going to check the model loss and model accuracy. And then you see the outputs just overwrite each other. And then here, there's an image. It says, in a nutshell, stack more layers for more complex scenarios. However, just there's an asterisk to that. Though you're adding more layers, that doesn't necessarily mean that your model's great, right? Say if you're like testing your data on like in production, and then you get some new data in, and you see that your classifications are incorrect, and yet you see a high accuracy. It's like, what happened there? Maybe your loss value was substantially high, as Bill said. That breadth of classification is just wider or larger, kind of like variance happening right there. So again, adding more layers doesn't mean that you're always going to have a great model that predicts future instances. Any questions on adding, or excuse me, on deep neural nets, kind of like right now? It's pretty brief, right? And that's amazing because you can see the power, or not the power of Keras, but just like the convenience of it. And imagine trying to do this in TensorFlow. Me personally, myself, I have not used TensorFlow, but after using Keras, would I want to use TensorFlow? Maybe, if I had a more complex situation, and then maybe I needed to go through my process more carefully, right? Because with wrappers, you don't have the luxury of doing more customizations. So kind of keep that in mind when using wrappers. Yeah. All right. And then right now we're going to take a quick break. 15 minutes for you guys, right? Yeah, cool. Take a break, and then we'll go through and start the student exercise. If you want to start the student exercise now, go ahead. But I recommend taking a break. Just relax. I get to eat this solid. I've been staring at it for a while. for exercise 4. For remote users, we're back. We have 10 minutes to do the folder 4. The exercise from folder 4. So go ahead and do that. Yeah. In this case of working with this classification, all you need to do is just create a function. Yeah.
Plug in the stuff that you get is different from the boilerplate.
Number of layers you want. Yeah. Interesting. With like this comprehension or like a for loop, right?
Yeah. I don't have to do this all over again.
It's pretty smart.
It's pretty much just a black box. I don't have to care about what's going on inside.
Okay. Yeah, no, totally believe that. Again, that's the convenience. So we're about to start soon. Let me just check up on. And then we're about to do the next exercise. Okay. So, remote people, sorry about that delay. I was eating whatever. I love my food. Yeah. All right. So we are on the where was I on? Folder 4, right? I'm just gonna assume we're on we're on folder 4. Is it working? Okay. Did you do conda update -f TensorFlow? Okay, cool. So there's that option. I forgot to you can force your update. That's a possibility. I think that's what I did like a month ago. So everything I said for the update, except in between, you'll do -f. In the resources channel, you'll find that little snippet of that command. You can try that out. If that doesn't work out, do the uninstallation, reinstallation, or if you're doing it right now, then go proceed again. Continue.
Saying that the softbox module is not saying access it. It's something that module is there.
It's just that the module has it's like a parameter.
Yeah.
It's not in the old version, but only in the new version.
Yeah.
So only if you are using a new version, you can use that parameter.
Then on the update, that package should solve it.
Yeah, it should solve. Yeah.
But it said it's all update.
Yeah. So yeah, I'm gonna continue on.
So yeah, that one is better to hang.
Yeah. Okay. So sorry for interrupting you guys, but I'm gonna continue on. So here, gonna import the modules. Seen before. We're gonna create our data set with our X matrix of our features and our Y vector, the target, right? So go through that, create the visualization. We see a nonlinear data set, right? And then for this data set, we're going to go through either with a neural network or deep neural network. In this case, we would want to use the deep neural network just because we have this complexity of a nonlinear data set. So we're going to go ahead and do that. Before we do that, there may have we're going to partition this data set into training and test subset data sets, and we're going to do our pre-processing for both the features and our target vector, and for our features, again, standard scalar distribution. Just trying to drill that in you guys' head. Sorry about that, but I feel like that's a great way of reinforcing is bringing upon those same ideas and just kind of cementing those set ideas. Yep. So we're gonna do this train test split. Instantiate the standard scalar object, fit the data for the training data for standard scalar, and do our pre-processing by transforming. And since we don't have a target vector with strings, right, we get to skip the encoding portion, so we can just go straight to the one-hot encoding, in which our output would be in one-hot encoding a target vector of a series of vectors inside it with true and false values. And here we create a normal neural network with 2 inputs, 6 nodes, and 2 outputs. Our model is sequential because it's a classification neural network model. I'm sorry. And then we go ahead and create the input layer, hidden layer of 6 neurons or /6 nodes, and then do our output layer of 2 units with an activation of softmax, activation of ReLU in the input and hidden layer line right there. Model summary, shebang. Our total parameters is 32. We compile our model, optimizer being Atom, our loss function, categorical cross entropy. Remember, if we're doing a regressive model, we would use MSE, or mean squared error. Okay, and then we're gonna fit our data. 2 kind of parameters you know here again, epochs, and shuffle. With that, and remember shuffle for every epoch, we shuffle our data so that way the weights in our neural network are adjusted in this forward and backward propagation. All right, and so we're going to compare this neural network with a deep neural net. I'm going to go pretty quick on this. Shift Enter. The only thing we're doing right here is adding that additional hidden layer with 6 nodes. With that, model summary. The carbonated wires got me. Total parameters 74. Those are probably too many. Ignore my solo comments to myself. Deep model.compile. We compile our model with an optimizer function Atom. Categorical cross entropy, as I mentioned before. I'm going to quickly go through that. See in this deep neural network how fast our accuracy is growing with the a lesser number of epochs. And then we're going to compare the models. You can see here deep neural net accuracy is 0.86, in the neural net 0.83. And then let me just quickly check so we see this nonlinear data set. See if we have this as an option to kind of like visually look at. Here's like a nonlinear data set kind of similar to what we just saw above. Oh, like right here. And then let's look at 6, 6, and 2. Okay, gotcha. Okay, that's already all there. With this data set, activation ReLU, kind of imagine this is what we're working on right now in this moon exercise. And you see our test loss, training loss is rapidly decreasing, and the classification is it's going, it's happening. That box is like 300 something right now. The computer's running fast for some reason. Anyways, but yeah, you can see like this classification. It's okay. Okay, and this is a little more complex scenario, but kind of reinforcing the idea of a forward propagation, backward propagation happening with 2 hidden layers. I'm curious what happens if we try to add more hidden layers. The third one. Super curious. Nothing. Let's try another one. Oh, a bunch of layers. Okay. So you see,
Please one more time explain how we can connect what we did in this program. How it connected. I can connect.
yeah, definitely. So unfortunately, with this playground, we have 4 data options, so we can't quite.
Only for data.
Yeah. So here, say I want to look at this this type of data set with this little spiral, right? And what I that I quickly showed, we have a input layer of 2 nodes and a hidden layer of 6 nodes. So right there in that one line we just saw, 2 input layer.
And we have to pick that one.
Yeah, because that's something of a non-linear data set closest as I can see to the other one. In reality, it's kind of not. It's really way more abstract than what we see. Sorry, here. Okay, so we have
6 layers.
six nodes or neurons. Yeah, and then we're gonna add another. Oh, sorry, in our deep neural net. But yeah, you'd be correct. For if the hidden layer, or excuse me, the output layer 2, that's correct. So here we have our second hidden layer, 6 neurons. All right. So let me just do that. And then output of 2. Right. And so kind of bringing the comparisons between each other, not quite, we see this classification occurring where the test loss, the loss value is decreasing, as you would see. Down here, right? That loss happening right here. And you see the classification happening right here, and the model itself is trying to do its best to make this classification happen.
With the playground, you can't control the activation for each layer.
Each layer? No, it looks like it only does it as a whole entity of those hidden layers. Yeah. Would you want me to try a different activation? Okay. Yeah, definitely. So let's try that out. See if we can have a better classification. You can see it's a lot slower, right? So here your model just kind of depends on, and is dependent on your data set. Here, white and blacks. Yeah, but did I kind of bridge what we're doing right now to what we're visually seeing? Yeah. I wish this data set was exact to what we've seen above. But if you go to the first everyone exercise we did, I think it was 2 or 3, and you choose this data set, you'll be able to see that visually. Yeah, and in a break, or if you have additional time, I can show you.
And we have million models, and only took 4 data sets, and we see everything exactly the same result.
For this data set?
We have only 4 data sets, and that's it.
Oh.
It's only for this.
Yeah.
This playground that can so they have only 4 samples. They are not limited.
Yeah.
This is what you see usually.
Yeah, and then these are some kind of like common data sets that you may see in educational courses like this, maybe like in data camp as well, or like Udacity, EDUX, etc. They'll have these basic type of data sets. Yeah.
When you say classify, what is that?
Classification of like the spiral.
Like,
Yeah, that's
Because it's not a linear data set.
Yeah. So Sky, maybe something as non-linear as maybe like tracking weather predictions. Maybe this data set can visually be that kind of like data collection of like weather information. There's a proper term for weather, science of weather. I forget. But yeah, that's one example. Spirals. I've seen in my past in college where like professors just show you some wild example. Yeah, but in regards to connecting this to a real world scenario, I can't say what that would be. In probably this case, right here, I know that for me myself, say you have some three-dimensional graph or three-dimensional graph, and you have a bunch of data points in this three-dimensional graph. Like, right, a bunch of data points happening right there. So if you look, say you're standing on top of this visualization, you're looking down, you can see this like inner cluster, and then this outer cluster happening right there. And then the way mathematically you can go about that, you can compute that like through some like complex algorithm, or I can kind of do a kernel trick or a transformation of a three-dimensional kind of data set into something two-dimensional. That's yeah. So that's like one example I have there. I remember just because of kind of like that vivid visualization, just looking down. Yeah. Any questions about like relating the data set of moons and this visualization? Cool. Oh. Okay, yeah.
So
yeah.
The deep learning part, we use the model and then fix the ratio, and then we add 3 layers.
Yeah.
And then first 2 layer is 6 nodes, and then the third layer will be 2 nodes.
Yeah.
Is that what I call?
Yeah.
And the first layer has input DIN or 2 because it's feeding 2 data into the first layer, right? Is that what DIN is for?
Yeah, the input DIM. Yeah, so those are your input layer. So in that first line, simultaneously you're instantiating your hidden layer, the first hidden layer, and your.
So you can refer to the little tangential thing, right?
Yeah.
The 2 DIN is like x1, x2 feeding into the first layer.
Yeah.
Right?
So that first line is the encompassing portion right here, which is your input layer, your hidden layer. That second line in this neural network, 3 layers.
So the second line is into another 6 nodes.
Yeah.
It's not required input DIN because they align already for the layer we just added, and then the layer we're about to add.
Yeah.
And then for the last layer we added has 2 nodes.
Yeah.
So do we add 2 nodes on here?
For this data set, there's the assumption of 2 classes. So those are your 2 nodes right there. Sorry, 2 classes. So it's going to have two nodes. Yeah, for those 2 classes, right?
So what's the difference between ReLU and softmax? Why do we use softmax ReLU for the 2 6-node layer and then use softmax for the last?
Yeah, definitely. So ReLU is an activation function related to going through the calculations within your hidden layers, right? That's all being done. The weights are being adjusted accordingly using this activation function for the nodes in these epochs. And then your activation function in your output layer, softmax, right?
Yeah.
that's used. That activation function is used for classification or optimizing your classification of your classes. So there's and then for your output, the activation functions that are available to you would be not really and all that. It'd be 10 of H hyperbolic tangent. It's mathy words. And then there's softmax, and then there's a couple other ones.
So,
yeah.
So can I assume that softmax is what allow us to transition from value nodes into an actual output?
I'm sorry.
So like, so if I don't put softmax layer on the for that one, it will not work, right?
You need an activation function. If you do something other than softmax, then you're not optimizing for your output. Say if you do 10 of H, that's great. And I explained it in and I sent a link in the general channel or a random channel showing some articles. The second bulletin, it kind of explains what this is. But I'll explain. A hyperbolic tangent would be perfect for multiple classes. So you have A, B, C, D, E, F, G. Softmax is great for classifying classes from 2 classes, A and B. Yeah. And then you would need a activation function for that output layer.
So the order of this code matters, right?
Yeah.
So I have to add the layer with the dim, 2 dims, and then I have to add a layer that if I want a deeper layer.
Yeah.
And then I also need a layer that actually brings the information out, which is the softmax one.
Yeah.
Okay.
Yeah.
Thanks, man.
All right. So on to the next exercise, and let me just take a brief moment, I think. All right. So we'll do the folder 5 independently, or you can do it in groups for 10 minutes. It's deep voice. Please get started with that. And then I'm going to try to skim through that or kind of like detail that pretty quickly. Kind of talk about saving models, what that is, and then get into the basics of that unsupervised learning. So yeah, 10 minutes. I'll put like then you can help with the issue if you need to. Oh, that's not good. Oops.
Oh, well, how do I? Yeah. And I'm sure that I'm not the first one to come in. You're the first one. So the first one to ask you. Any idea? Or should I just start Googling? Okay. Yeah, I went to Google the era. And then it's like, oh, yeah. Okay. Internet era. I think the choice changed. You don't need to find it. Because I don't see a sign in. So when you, is there a sign in here? Mm-hmm. Yeah, when you do fair, it's a blue topic. It will immediately sign in. It will. Huh? Yeah, it will. No. It doesn't. It gives me an error. So that's kind of where I'm at. Like, okay, I've done the work. I am impressed with the tablet inability for me to save my work. So at this point, I'm somebody's not five tablets, sure. You could. But that should be the other way. I need my. I get into them, I think. No? So then you have an error. So they know when you solve it,
you close it up, but I know you would lose.
So,
Maybe
so
you
you can't tell me this is a production piece of software if I invest a full day's worth of work and I can't save it.
I think it should automatically save it. But I haven't tried before.
Because
Yeah.
you just, a professional software programmer would not grab that. They would not. Sorry. So it becomes a matter of, at this point, it's just random.
Oh, yeah. I wonder if you can close it and then when you reopen it, would it automatically save? There's a high chat, kind of like, you know, like Google Chrome, it saves all your tabs. I wonder if you like that.
Do I feel lucky? I should just have you grade it right here. Rather than turn it in. Go through it. And then
Yeah, we got maybe that great.
because especially if I don't know what I did wrong, I'm just gonna put in. So at this point, I'm not do I just kind of flush number of hours of work?
No, maybe you can just explain what you did to me.
Okay.
Then like just the process. So because this thing open, so yeah, like, it could be anything. So what do you
So story was what the most frequent trip. Yeah. So,
You can submit it.
I'm gonna
Yeah.
have a conversation. Say. Sorry. Thanks.
Oh, that was
She changed the website, yeah,
we'll find
That's
out.
why that's an error, so I changed it to 20.
Was there instructions for sampling the data, like being like too specific or some specific amount of columns?
No, in here it says 21 columns and it's using with the index.
Oh no, what I mean was the instructions. No, there's like a.
Error message?
No, I mean there's like instructions with the columns. If not, it's totally cool. No, probably not. I'm about to go through the solutions right now. It's 20.
What I don't know is.
You guys. Yeah. Yeah. Remember, we got 15. Thank you. Oh, no. Thank you. They're the best. They're the best. Huh? All right, so sorry to intervene, but I'm gonna go over the solution right now. 15 minutes. I'm gonna try to briefly cap on how to save a model, then how to load that. It's pretty simple, just like this this wrapper, Keras wrapper. And then I will get to the unsupervised learning concept or algorithm that I mentioned initially. So let's get started. So here we got the voice gender recognition data set. So think of having all this audio information, converting that into data, and then from there we're going to classify this data, or maybe in the, I think there was labeling here for this data, actual data. Okay, yeah. So we here, since we have strings for our target vector, we would have to go through and do our encoding and then our one hot encoding. So let's get through that soon. Oh no. Okay, so imagine I did run that piece of code right there, and the data set did pop up like you're seeing right now. I have an LFS error. I'm gonna not troubleshoot that for the sake of time. So, but luckily I have the outputs from whoever created this Jupyter notebook. So cut the intermission, proceed. Here for this X, we're going to drop the label column, or that target column. And then we save that. We do our shape. It's 316. There's about 3,000 rows, 20 features, as some of you noticed. For the 20 features. And then here we got your target vector. Going through, kind of go through the same iteration of pre-processing, right? We do our train test split. That's not part of pre-processing. But coming up, we do the encoding, label encoding for male and female. And thereafter, after that transformation of this encoding, we do the one hot encoding using keras.utils, seen above. Using that two categorical method. Here we create a deep learning model. I just want to make that sound cool, but I don't have that masculine voice to make it sound cool. So yeah, it's whatever. Here we go through in this first line, creating the input layer and first hidden layer. The number of units for this hidden layer or neurons is 100. Your input dimensions is 20. Yeah. You can make your model howbeit initially. It didn't have to be 100. That's kind of like the whole point of hiring ML engineers and even these AI experts is not only to like implement your model, understand the domain and everything. Just before this kind of like emerging industry, there was a lot of fine tuning until a lot of people recognized that, built packages for that, somehow like grid SV search from at your ML concepts of supervised learning, where you put in some parameters in there, you let the model run to find the most optimal parameters. So there's things like that to kind of like leverage you not wasting your time or fine tuning your model.
There's ML on top of your machine learning. This is how I think about it. Is you have your model.
Yeah.
Your model has certain hyperparameters.
Yeah.
And then you just say, well, I know how to do machine learning, so let's do machine learning on my hyperparameters.
Yeah, let's go with that. Yeah. No, it did. It's just part of me is like yes and no, but like even then I can't even debate on that myself. So
I don't know how they do it.
No, but it's a great analogy, right? Yeah. So going through, a lot of you recognize that your input dimension should be 20, not 2, just because of the number of features you have. Or it's a 3,000 row by 20 column X matrix. Sorry, X variable. And then we compile using optimizer, loss function, the metrics we want, accuracy. We fit the model. And here they did 60 epochs or epochs. Shuffle is true. And here you see that the normal neural networks loss in accuracy and the, okay, there's no deep. It's probably a typo. Yeah, it's totally a typo. Yeah, it's supposed to be a deep neural network, loss in accuracy values for that. And then here we do use predict classes to predict some like an array like one value. And here kind of look a little at addendum. So say for your values, you don't want to see a bunch of like ones and zeros, right? You want to see like, okay, for in my prediction, I want to see what were those predicted classes. Here with our original label encoder from sklearn.preprocessing, we can do a dot inverse transform of the one hot the output right here from one hot encoding, right? This array of arrays, if you will, or yeah, array of arrays, particularly like 5 of them, and do an inverse transform and go back to our classes. And here we compare those respective values of the predicted classes here in our predicted labels and our actual labels. We see here that there's a great estimation or prediction from our model. Any questions on this little portion right here, inverse transform? Solid. Cool. So now I will cover, after this inverse transform, I will now cover how to save a model. So as I'm opening this up, a lot of Kaggle competitors, sometimes when they win, and a lot of people are interested, saying, "Hey, how did you do that? How did you, or what model did you use, or what were your hyperparameters, or your parameters? Excuse me. How, like, what did you do to create this model? You can save your model, give that to your companions or whatever. In this case, this Kaggle master, excuse me, this Kaggle master can share his model, distribute it, and other people can use it for either retesting, improving it, etc. So let me come to the folder right now. So here in the solutions, we have the save model. It's a .h5 file. That's HDF5 file format. And what it is, it's rather than just like a flat data set, like a CSV or however you be it, yeah, whatever it may be. And from what I understand and what I read in documentation, an H5 or HDF5 file format is a container of information. And that being said, you would want a container of like all your information, such as like the parameters, your layers, all these things that are coming into your deep neural network or your neural network. Kind of like a question I thought myself. Maybe you can research yourself. I haven't had the time. Why isn't it a JSON format, right? Where you can have in this JSON like some portion where it's a dictionary inside this a dictionary of attributes. Why not have that, right? It's a question I've had for myself I didn't answer. So I'm going to go this pretty quickly. This model.save is going to occur towards the end after you do your fit. So skimming. Here we add our layers. This is a deep neural net. Compile and fit. Well, I didn't do something up there. I'm going to skip that. Here we do an evaluation, but after your fit, you can just save the model if you want. But here you do a model.save. And then the name of the file, directory, of course. Right, like you do in your, I read CSV. 2 CSV, or like kind of equivalent of pandas. And you just make sure you save that H5 file. Now to load it, this model, once it's saved, say I'm like a friend that wants to check out learn deep learning, right, or neural networks. From Keras.models, instead of importing your sequential or the equivalent regressor model, you would just do load model. And then, yeah, load model, the directory of your H5 file. There, you have your voice, you have your model, and then you can do your evaluation. So that's what how saving the model works. Model.save, and loading the model. Simple, clean, loading the model. All right, for 6 minutes. Rather than doing the after exercise for unsupervised learning, I'm just gonna go straight to that solution. Yeah, sound good? All right, cool. I don't want to leave you guys without kind of knowing what unsupervised learning is. So unsupervised learning is say you have a data set with no features that are no labels for your features, but you want to make some predictions. That's what unsupervised learning is. There's several different type of algorithms for unsupervised learning. K-means is one of them. This is not k-nearest neighbors. That's for supervised learning. K-means is for unsupervised learning. So just kind of like reminding you guys about what KNN, totally different from K-means. Yeah. Here, we're going to visualize our data. Our data is from sklearn. It's going to have clusters. There's about 4 of them right here, right? What K-means does is allows for classification of this data set in like clusters for K-means. Yeah, so the number of clusters we're going to use are 4, the K value. And we can see from the plot above, again, there are 4 clusters. And we're going to instantiate our model with a parameter, the number of clusters being 4. We're going to fit our data, predict, as we've seen in almost every other sklearn concept. Yeah. So k-means.fit data. Whoa. We're going to fit the data. We see these parameters right here. We're going to predict, make a prediction, right? And then here we're going to visualize the same data set, but we're going to color it with our predicted clusters. So it's predict, right? And shebang. We see the colored clusters. I realized this was the instructor portion. Let me just quickly get to the student one because it's a little bit more interesting. Something I want to point out. So here we have, how many clusters do you think we have? 6, right? Yeah. Great. And then for some reason, as we're going down and we're about to instantiate our k-means model, the author put 12 clusters. Interesting, right? You're not restricted to the amount of clusters you're trying to use, but it's a great idea to visualize your data set. Say if I didn't visualize this, I put some like number of random clusters, accuracy might not be so great, and misclassification will occur, or false positives would occur in your confusion matrix. I sent that out in the 3rd bulletin in the random channel, I think, or general channel. It's in those like little resources I sent. Anyways, so let me run through this. We're gonna predict clusters here for the same scatter plot. Right here, we're just gonna color our data based on these predicted clusters. As you see in the output, we have a lot of misclassification, right? Or for these supposed 6 clusters. So let me change up this parameter. Yeah, so let's try 6. And let's see visually what these clusters would look like now. So at the flash of an eye, you see that the classification for these clusters are made, or the number of misclassifications is tremendously decreased. Huh? Okay, yeah, sure. So let me put 24. You see this a larger partition of clusters. You see more clusters, right? That being said, it's more granular, and you're not really generalizing your data set, and therefore you're making more misclassifications, right? Yeah. So and then towards the end of this, quickly, you'll just see what k-means is. Like, why is it called k-means visually? So let's go through that right now. So we have the cluster centers, which would be like right here, right here, right here. Those are the means of each cluster. And then the labels. So let's go through and get these centers. We have the x and y values for every cluster. Here we have 6 rows, and we're gonna visualize this right now. As you see right now, this is the case of the clusters being 12. So yeah, 12 clusters, and you'll see 12 means happening right here, or showing right here. Here, 6 clusters, 6 means for these clusters, and you see last misclassification for these clusters. And yeah. Any remaining questions? Yeah, so k nearest neighbors is more of for the number of nearest neighbors. So, you guys, for these 2 nearest neighbors, which group do I belong to, based on kind of like the distance? So who's closer to me out of these 2 neighbors? Which group am I part of? It looks like I'm part of like both, but I don't know. But anyways, so say I have like 20 neighbors, or I don't know how many people. Yeah, and then the clusters here is just some classification of. Yeah, exactly. Yeah. And here kind of like asterisk to my my teaching right now. Do some research on this. I myself don't have like a great grasp of unsupervised learning, obviously, and then also deep learning. So do take advantage of like learning more about this information. Yeah, and then again, unsupervised learning, k nearest neighbors, supervised learning. It is 9:30. Yeah, so you guys are good to go. Yeah, no problem. Yeah.